So today we are talking about something that we have, you guys actually already know because we've talked about it before and we did a lab on it. And that's the idea that voltage and electric field are related. All right? So let's consider a mountain. Now, who's been on a mountain before? Raise your hand. Oh, wow. You know, I asked 7th period and no one raised their hand. It's like, wow, what a bunch of Illinois flatlanders.
You also have like 9 people in your, maybe not even like 8.
I know, but that's crazy to me.
A smaller sample size.
Anyway, yeah, it's that living in Illinois, you really, I don't know, when you go somewhere else, pretty much anywhere else in the world where they have mountains, you see that for the first time, it's just so different. And it was one thing when I moved here that I was like, wow, you look out on the horizon, there are no mountains anywhere.
Literally like the base of the mountain, right?
Yeah. Well, where I grew up, it was mountains and ocean, and that was it. So, anyway, but if you go on a mountain, or if you spend any time on mountains, you're going to become very familiar with something called contour maps. All right, and contour maps are basically what you did the voltage version of. But the idea is, let's say you have a mountain, set of mountain peaks that looks like that. The contour map for this, if you draw all the elevations from like a top-down view, is going to look something like this. All right? So if you're standing on the front side of the mountain and you dropped a ball, which way would the ball roll? Down, right. If you're standing on the back side of the mountain, which way would the ball roll? Down, right? But in this case, down would be up the page. If you had a ball here, which way would it roll? Down, right, to the right. And here it would also roll down. We mentioned before that the electric field is actually the downhill direction on the voltage plot, right? Okay. So if you ever want to draw electric field lines, if you've got voltage lines, how do you draw them?
Perpendicular to
Yeah, because downhill is always going to be perpendicular to the level, right?
Yes.
So if my level is here, if I'm standing like this, downhill is going to be that way, which is perpendicular to that. If I'm standing over here, downhill is going to be that way, which is perpendicular. Does that make sense? Mm-hmm. All right, cool. So electric field is the slope of the voltage in the downhill direction. But the thing is, if you look at it from the top, downhill is direction changes. All right? And moreover, if the voltage lines are curved, that means the downhill direction line is also curved. Right? And I did kind of an example of that in blue here. Downhill, goes from this mountain peak, it follows down here, and then curves a little bit out. And I tried to always make the blue voltage lines perpendicular to the the blue field lines perpendicular to the black voltage line. Does that make sense? All right, cool. Now, mathematically, if you're in multivariable, you know that this is a gradient. If you're not in multivariable, you know that the direction changes, but the slope is a derivative. And since we're interested in the down, not the up, it's actually the negative derivative. So, electric field is negative derivative dV over dr. Good, where r is the downhill direction. All right. Now, if you rearrange that equation a little bit, solve it for dV, you'll have dV equals negative E dot dr. Wait, what's that dot doing there? That's a dot product, right? Okay. Yeah, it's a dot product. I'm going to ignore that for now because I don't want to get all multivariable-y. But it's E dot dr. That means if you integrate the total voltage change, actually I should have written that with a triangle in front of it. the voltage change from one spot to the other would be the negative integral of the electric field over the distance. All right, units check. Make sure the units can't check out. We know electric field is force per charge, which is newtons per coulomb. We also know electric field is dV over dr, which is volts per meter, which means 1 newton per coulomb has to equal 1 volt per meter. Did we talk about this before? All right, so I think I mentioned that before. Okay, so that's the basics. Let's apply it to some problems. Remember how I promised this weekend was going to be nightmare problems?
Yeah.
Well, here they are. We are going to redo shell problems. All right. This is the basics. Do you remember doing a shell problem in the last unit where you figured out that the electric field inside an charged insulating sphere goes up like this on the inside and then decays away on the outside?
Yeah.
What if you wanted to figure out what the voltage did? Is there voltage inside a charged insulating sphere?
Well, looking at this
Yes.
graph, I'm reducing
Why?
gas.
If there's a distance for like the radius.
There's charge.
Let me ask you a different question. Let's pretend you're looking at a Van der Graaf ball. You know those are hollow, right?
Yes.
Let's say the outside of the ball is charged up to like 50,000 volts. What's the voltage on the inside of the ball?
0. No, not zero, not zero, because it's. Oh, hold on. Oh shoot.
No,
How do you
because
explain
voltage
it?
isn't a
Like
vector quantity. It's a
Yes,
scalar.
scalar.
So yes, there is
There is.
voltage inside
There
the ball.
is voltage inside the ball. How much?
A lot.
How much? Give me a number.
The smallest is in the middle.
The smallest is in the middle. What?
No, the
No,
greatest.
wait. The greatest
is in
is.
the middle.
I have that backwards. The greatest is in the
The
middle.
greatest in the middle. What?
Okay, I don't know.
What's the electric field inside the ball?
Zero.
Zero.
Zero. So if there's no electric field, that means the voltage isn't changing, right?
Right.
Yeah.
Oh my
So
goodness,
in the
Tom.
middle of the ball, guess what the voltage is?
50,000.
50,000 volts.
50,000 volts.
Everywhere inside that ball, the potential is at 50,000 volts. Doesn't matter if it's hollow or not. Just as long as all the charges are all around the outside, the inside, if there's no electric field, that means the voltage is the same everywhere. And if it's 50,000 volts on the outside, guess what it is on the inside?
50,000.
50,000 volts with zero electric field. Does that make sense, Sean Patel?
Yes.
Now,
So what's different about an insulating sphere?
why is an insulating sphere different?
Uniform charge distribution.
Are charges on the inside?
There are charges on the inside for a plastic insulating sphere, right? So if there's charges on the inside, doesn't that mean there's electric field? And if it's a positive charge, is which way the electric field point? Outward, right? Okay. So if the electric field points outwards, that means the downhill direction is outward, which means uphill is inward, right?
The greatest is in the center.
So it should have the greatest voltage in the middle. Good?
I think Jack was 50% right.
All right. So
I know.
here's what it looks like. The electric field linearly increases, right? We know this. This line right here, we figured out because we've now derived it. We derived it when we did the falling through a planet. Remember that? Then we re-derived it again in the Gauss's law unit. And so we know how to do that linear increase, right? Well, if the electric field is linearly increasing, that means there's got to be some voltage in there. And moreover, the voltage has to be changing because there's an electric field. So all you have to do is integrate KQ over a squared times r, this one right here, to get this curve. Oh, by the way, if this is linear, what's this curve going to be? That's got to be a parabola. Wouldn't you agree? All right. So here's how you do these problems. The key to doing problems with voltage, these concentric shell problems with voltage, you always start at infinity, at the distance of infinity. Why do you start with the distance of infinity when you're dealing with voltage?
0 is there.
Because that's the starting point. That's the 0 point. You integrate backward from infinity. Start here, integrate up to get to this point, to get the voltage value there. Then once you know that, then your function that you're integrating changes, right? So let me go down. So, starting a to infinity, actually I should have done infinity to a, right? Figure out the voltage as a function of r, ends up being kq over r. Now, at point A, we know that the voltage is at kq over a, and we use that to solve for r plus c. So we integrate the inside electric field, which is kq over a cubed times r dr, and then use this point to solve for r plus c. All right, so that's the process. Yes?
For the second, this graph, the slopes of this graph should be the values of E, right?
Wrong. The slopes of E should be the values of voltage. We...
No, not
Oh, sorry. Yes, I'm an idiot. You are right. The slope of the voltage is the value of E. Right. But negative.
Oh, but negative.
Right? It's negative. So if you look at it, and the question someone was asking, let's see, what's the slope here, right here? What's that slope? 0. So what should E be here? 0. Guess what? It's 0.
That's crazy.
Now what happens to the slope? It gets more and more negative. So E has to get more and more positive. Got it? All right, so that's it. All right, so we're going to take a look. I'm going to let you get you started on these as soon as I can. But before we do that, we're going to take a look at problems 1, 3, 5, and 7 in your packet. That's it.